How do I share the screen?
I stopped sharing, so you.
Oh, here it is. Yeah.
Yeah.
Okay. Yes. Can you see this?
Yes. Yeah.
Okay. Yes. So my talk today is entitled "A Representation of Artificial Spin Ice for Evolutionary Research," and I'm sure people here are very comfortable with ideas of evolutionary research and evolutionary algorithms, but mostly this concept of artificial spin ice is probably unknown to a lot of people. So I thought we'd start by looking at what that means. So the name artificial spin ice actually hides a lot of history in it. So to kind of misuse computer science terminology, we can kind of curry it and try and understand the individual parts. So if we start on the very far right here, we have your kind of bog standard water ice. And I'm going to be very brief and vague about the physics here. But basically, all we need to know about ice is that these water molecules, when they fit together to make this lattice, because of the slight charge discrepancy between the oxygen side and the hydrogen side, they have certain ways they like to be fit together, basically, when they're in this 3D structure. And we call the kind of rules that govern how they like to be put together the ice rules. And so then if we follow this arrow down, we can move from ice to what's called spin ice. And so here we have, I think this is a crystal of pyroclore, so it's a magnetic material. And here we have these blue magnetic ions. And what was discovered in spin ices is that the spins or the magnetic moments of these magnetic ions, the direction they point is actually governed by the same rules as in ice, these ice rules again, or analogous ice rules. So that was very interesting. And then finally, we can move much further into the future to artificial spin ice over here. So now we've got away from this kind of bulk material and we're into these discrete nanomagnets elements. And so these nanomagnets are shaped such that magnetization can only lie along this long axis. So this magnet, for instance, could either point upwards or downwards. And this is, again, a kind of analogy to these spins in these other systems. And the spin of the magnet is kind of determined by its environment, and these spins change and they interact with each other. So it's kind of a self-organizing process. And so artificial spin ice was initially just a kind of a model system to study these kind of systems. But really, in recent times, it's become just of interest as a substrate by itself. So why are we interested in artificial spin ice? So there's the physics, kind of material physics and metamaterial side of it, which is, as I said, it's a model of these frustrated systems, such as spin ice. And also we see very exotic material properties in it. Through kind of tuning the position of the magnets in this artificial spin ice, you get very different global behavior. But more interestingly to us, perhaps, is the idea of computation. So as I mentioned, the spins in the lattice, they do this kind of self-organizing, and through this local interactions, we get this kind of different emergent global properties. So yeah, anytime we have these kind of local interactions and with emergence, it's kind of a sign that there might be some fertile ground for kind of unconventional or material computing. So if so, then we have low-powered computation and memory. There is literature already on using artificial spin ice as reservoirs or for ballistic computing. And then kind of tangentially, there's some work done on kind of using a very small number of nanomagnets to build logic gates. So here are some of the commonly studied artificial spin ice geometries. A geometry here just means any arrangement of nanomagnets. So we have square and Kaguma on either end, and these are very much kind of analogs to real physical systems. And then in the middle, we have this kind of more recent discovery, which is a pinwheel geometry. And that's just the square geometry, but you rotate everything 45 degrees. And actually, this small change means the global dynamics of the system are very different. So in square, we tend to see the global behavior demagnetizing itself. So you have net demagnetization. Whereas in pinwheel, what you see is you see regions of kind of highly magnetized areas. So the geometries, the way you position these nanomagnets really have a huge impact on the system as a whole. And so in the literature, what we've seen is there's kind of two kind of ends of the spectrum. There's these kind of patterns, geometries, which are very simple. There's some slightly more complex ones, but generally it's kind of tilings or these kinds of tessellations. And they're very much kind of human designed. And then there's the kind of opposite end of the spectrum, which is where people are kind of randomly placing magnets, doing like random sampling to sample the magnets' positions and angles. But there's not really any kind of in between, and that's what we're interested in. Is there, can we kind of use a computer to design new geometries that fit a certain purpose? So for that, we turn to evolutionary algorithms, just because they're generally a good thing to use if you know the task in hand, but you're not really sure how to achieve it. So for that, we turn to evolutionary algorithms. In order to do an evolutionary algorithm, we need to be able to do these 3 steps. And to be able to do that on artificial spin ice, we require some kind of a representation of them so we can mutate them. And the kind of requirements for this representation, or the desirables, are that we want it to be scalable. Geometries in the literature are often studied at different scales and sometimes very large scales. So these are quite small, but it's common to want to go to kind of thousands or millions of nanomagnets. So we would like a design that's scalable. So we're already kind of thinking in terms of developmental generative processes for this design. And we'd also like the ability to do smooth mutations. So if we have, if we make a small change to the genotype, we want this to be reflected as a small change to the produced geometry or the phenotype. So kind of shooting ahead into the future, we found a representation that we were happy with after much trials. And this representation, we represent an artificial spin ice geometry as a set of building blocks or tiles. It's tiles in quotes because it looks like a tile, but we don't really tile with it. But it's a good enough name for now, at least. And every tile consists of exactly 2 magnets, 1 origin magnet, and this is always fixed at the origin and has no rotation. And then we have this free magnet that can be anywhere in the tile and have any rotation. And so we could kind of distill all this information down to this triple here, just using the position and angle of this green magnet. But it helps a lot to kind of have this pictorial representation in mind when talking about how the development process works. So very simply, we have a magnet and we have a tile we want to apply to this magnet. And all we have to do to apply this tile is we just line up the origin magnet with this magnet. And then wherever this green magnet ends up, that's where we place our nanomagnet. So we can see this would be a tile application. And also we could rotate this 180 degrees and it would still match up with this. Okay, so we could also do this. And this would be the first iteration of our developmental process. And now we have 2 new magnets to apply this tile to, so we could do that. And there we go. And hopefully you can see what's actually been building here is the square spin ice geometry. And so in fact, each of these kind of elementary geometries can be built from a single tile. And you can see we can kind of go smoothly between them as well. In particular, we can look at the square and pinwheel. Hopefully this video looks okay through Zoom. But what we see on the left is the tile, and on the right is the geometry created by applying it repeatedly to a magnet. So, oh, and now time for a quick puzzle, so pay attention. If we wanted to create this spin ice here on the right, what kind of tile would we need? I'll give you 5 seconds to think about that. Yes, that's right. It's actually a trick question. We need 2 tiles. So if we just had this tile, we'd be able to produce kind of one long tower, but we also need this tile here to be able to produce the rows and kind of move into the second dimension. So that was just a way of demonstrating that in order to be able to produce lots of different geometries, we sometimes need our individuals to be a set of tiles rather than a single tile. And this is also, what's quite nice about this is it gives us a mechanism to control the complexity of the designs. So we can limit the algorithm to say only using 2 or less tiles or something, and then we get simpler designs. And I should just say this is an ordered set, so we always apply the first tile and the second tile and the third tile. And we never apply a tile if it would lead to magnets overlapping, because that would be unhelpful. And really the last thing to say about the representation is that we also can add in extra complexity by attributing symbols to the magnets. So you can say, like, if we want to apply a tile to this magnet, then it has to have a matching symbol. And we can go even further if we take inspiration kind of from parameterized L systems. We can parameterize these symbols. So we just go for a very simple parameterization here, but obviously there's lots of different things to try if you want. We just say that if this magnet is rotated less than 180 degrees, it has one symbol, and if it's more, it has a different symbol. So that's really the representation. Now we're back to the evolutionary algorithm, and we know what our population looks like now. It's kind of a population of things that look like this. So in terms of evaluation and selection, these are pretty straightforward. To evaluate our artificial spin ice geometries, we just construct them, and then we send them to artificial spin ice simulator. We use one called FlatSpin, which is we designed and is very fast. So evaluation is pretty straightforward, and then we can select based on some features we see in the simulation. And then for mutation, we can look at it in a bit more detail, but it's quite simple too. We just have two classes of mutation, really. We can take this free magnet and do something to it. We can move it or rotate it. And that's kind of like a gene mutation. Or we can consider the set of tiles and do a kind of chromosome mutation, reorder the tiles or delete or add some tiles and things like that. And then crossover is also quite straightforward. As you'd imagine, probably, we just take two parents and we kind of sample tiles from each of their genomes to create a child. So now we have the representation and we have the algorithm, and we're at the point where we can start to test it on fitness functions. So here we have, we're going to talk about this very simple fitness function. It's kind of analogous to the Max1's fitness function, if you're familiar with that. And we're kind of testing the resilience of the magnetic system here. So if you imagine we have some geometry here, it's not a very exciting one, but it's a good example. All these magnets are pointing to the right at the moment. But if we applied a strong field to the left, we would expect these magnets to flip like this and change their direction. So our task is then going to be for the evolutionary algorithm, can it come up with a geometry or an arrangement of these magnets such that they don't flip, or such that as few as possible flip? And that actually turns out to be quite an easy task. Actually, if we just position the magnets like this, orthogonal to the field, then they don't flip, at least for this shape of magnet. They're not affected by this field. So this problem is a bit too easy, so we can make it harder by having two fields. And now what we do is cycle the field like this, and then we cycle the field up and down, and we do this a few times. And now this problem has no trivial solution, basically. The EA has to make use of the local interactions between the magnets to hold them in place. And the only other thing to say about this task is it's important to notice that how difficult this task is it depends on the strength of these fields. So if this field is very weak, then the task becomes very easy because the magnets will just never flip, regardless of how they're oriented. Whereas conversely, if this field is very strong, then the task becomes very hard because the magnets will kind of always flip, regardless of how they're oriented. So because of this kind of field strength dependence, looking at this very messy graph, what we did here was these box plots are actually just a random sample of 100 random geometries with no evolution done at all. And this was just to show kind of how the task gets harder as we increase the field strength, which we call H. So higher is bad, of course, because we want to minimize the number of flips. So we see kind of as the field strength increases, this on this random population at least, the fitness gets worse. And now these red crosses are the best solution we found through evolution at each of these points. And you can see that we beat randomness at every stage, which is not too impressive, but it's nice at least. Down here, we've achieved perfect fitness of 0. Here, this is kind of the best you can do at the high field levels. So what's happening here is we're hitting kind of half the worst possible fitness. And this means kind of everything's flipping every other field cycle. So you can kind of imagine we've gone back to this kind of trivial case here where the magnets are just choosing to align with one field. And that way they flip every other field, basically. And that's how you get this lower bound here. But the most interesting region, I think, is this kind of middle region where we kind of, the random population have already gone off into this high flipping regime, but we were able to kind of stave it off for a bit longer. The only other interesting thing is where you have this little outlier here. So we performed a bit worse here than we did, say, over here, even though this should be a harder task. And actually, if we look at the kind of fitness over time, 0.08 is this blue one here. You can see it kind of, it improved its fitness quite quickly near the start. And I guess my hypothesis is this led to some kind of premature convergence and lack of diversity, which is why it didn't perform so well. But yeah, I think this is really just down to the kind of inherent randomness present in evolutionary algorithms, and not something to worry about too much. And we also can take this as a chance to study the scalability of the representation. So I think we take this, geometry here found at 0.07. It looks kind of like a square actually. And we say, what happens if we grow this to a larger size than what we tested it on in the evolution? So we tested it at about a size of 100 magnets. But this is a developmental process that we grow these geometries with, so we can grow it further and see how it performs then. And so when we grow it to 1.5 times, we still achieve perfect fitness. When we grow it to twice the size, we achieve 16 fitness, and this is where it becomes a bit hard to say what this means. We don't really have a base to compare to, but I would say 16 is still pretty good. When we get to 4 times, the fitness increases a bit again. Like, I think it's debatable at this point whether we say it's scalable. It's not too bad in my opinion. But then when we get to 8 times, then clearly the fitness has exploded and we're no longer seeing scalability in behavior, and the fitness has degraded. So is it scalable? I'd say definitely yes for the first 2, debatably for this one, and then no here. But there are possible ways to improve the scalability, and I will possibly talk about that at the end if there is time. So now we come to our other fitness function. The last fitness function was a kind of a physics material properties fitness function, whereas this one we're looking at a more computational measure, or at least a computational property. And again, we're going to use these 2 fields, but this time we're going to call this field 0 and this field 1. And this allows us to encode some kind of bit string. So we're going to fix our input bit string to this, which is somewhat arbitrarily chosen by me. Clearly there are patterns in it, but I didn't think too hard about it, I promise. And so what we do here is for each of these steps, we cycle a field. So we'd go 0 and then 1. And when we cycle a field, the state of our geometry, well, the state of the artificial spin ice might change. So it might do something like this. And what we're going to do over the trajectory of this is we're going to count how many different unique states we see. So here, the state is just the kind of ensemble of the spins. So we want to count how many unique states we see over this trajectory, and we're going to call this the state count. And so we have 20 bits of input. So we're sampling 20 possible states. So the maximum number of unique states we could see would be 20. And the smallest number would be 1. That would be if we saw 1 state and then it didn't change the whole time. And what we're going to do this time is, rather than search for any state count in particular, is we're going to do a novelty search and try and find as many different state counts as possible. So and again, it's important to note that this task is dependent on, the hardness of this task is dependent on the field strength. It's slightly less obvious this time, but you can imagine if both these fields are very weak, then likely the state wouldn't change. So we'd only see state counts of 1. And if this field's very strong, then what's happening is every time we apply an input, it's kind of completely overwriting the system. So we lose any kind of memory in the system. And so we'd expect to see kind of a state count of 1 or 2 because we have 2 different inputs. So this is what we do. We're going to do a novelty search to see how many different state counts we can get on this fixed input by searching for different geometries. And so again, we did this on a random selection just to test how the problem difficulty changes as the field strength changes. This time we want higher because, of course, we're trying to have as much diversity as possible in the population. We can see we're beating randomness in most places. There are a couple places down here, here and here. We lose out by exactly 1 point, which is a bit upsetting, but it's kind of happens after we've converged to this low diversity state anyway. So I'm happier it happened down here than up here, I guess. But what's really nice is at 0.07 we achieve perfect fitness. So that means for any desired state count, we can produce a geometry that gives that state count. And kind of also, just out of interest, we can actually look at some of the geometries that were created here by the algorithm, and we can see we have quite a fun, diverse mix of crazy looking geometries. We have some like very regular stuff like this, these kind of more curly, like recursive looking things. I don't know how well this shows up on other people's screens, but it kind of looks like a one-dimensional long pigtail thing. And this one's very nice too. We have like the square spin ice here, and it kind of smashes down here. So it's very nice to see this kind of diversity in the population. So now I'm going to start concluding. So we were able to search for emergent physical properties, as we saw before. We demonstrated we do have scalability in the representation. And by that, I mean, just we can grow these, once we have the genome, we can grow it mostly to any sizes. There are some constraints where we can't do that, but in general, we can do that. But what we also saw was that the behavior we evolved does not always scale, or at least it scales up to some certain extent. And we were also able to explore a variety of responses to encoded inputs. And we saw a nice diversity of geometries. I don't think that's how geometries is spelled. Which is important for artificial spin ice because we're not really sure what the behavior will be until after we've seen it, kind of. So for future work, pushing this scalability further, there is a few ideas we have here. One thing could be to incentivize traits that would increase scalability. So in the fitness functions, incentivizing self-similarity in the patterns, for instance. Or more interestingly, perhaps we could do as we did here, evolve some candidates at a smaller size, which is nice and fast, and then take some of the best ones and then grow them larger and then evolve them at this larger size for a small number of generations to kind of tune them up to this new size. And finally, what I think is most exciting is this idea. So there's previous work been done on generating zoos of ice structures using machine learning. And ice structures are a bit different to artificial spin ice structures. They're limited by these thermodynamic laws, which we are not limited by, really. We're not limited by anything other than magnets shouldn't touch. And so this is probably the reason why it's not been done before, because it's hard to say kind of when to stop when your zoo is full, if there's infinitely many structures. But now we have this representation, we have kind of way we've got a mechanism to control complexity and to say kind of how many structures we want to consider. And then very finally, this is what I think is the most interesting. I would really like to take this representation and use it as part of some kind of a novelty search as a way to kind of catalog these different artificial spin ice geometries using different, say, like computational measurements, for instance. And I'm kind of envisioning a catalog of artificial spin ice where you can say, you know, if you have a problem that's very memory intensive, use this geometry. If you have some kind of problem that needs lots of non-linear computation, use this spin ice. So that's about it. The last thing I have is just some nice pictures to show. So this is an evolved geometry that we were able to produce. So this is we produce this, and this is under an electron microscope to give a scale of the size. I mean, you can see it's 10 micrometers here. So the whole thing is about the size of a kind of like a very chunky bacteria or something, I guess. And then over here we have some other geometries. So I call this one the brain and this one the pizza. And these we produced, and then we were able to send them off to one of these kind of particle accelerator, like kind of large hadron collider style things. And we bombarded it with electrons, and that allows us to see the magnetic state. So this was just a way of kind of saying it's not all kind of still in silicon simuli. We're moving into the material realm. So I thought that was a nice thing to show at the end. Yeah.
Great, thanks, Arthur. Really nice. We have a question. What kind of physical interactions are modeled by interactions of nanomagnets and artificial spin ice?
Okay, it's a bit of a physicsy question, and I'm not a physicist at all, so I'm a bit scared about this question. But I guess if we talked about it right at the start, I think, if this is what you're referring to, this kind of, it's a long way. Yes, this in particular, but what we say is these systems are frustrated. So this means that they have ways that they prefer to fit together. So these spins have ways they prefer to align. It's kind of like, pushing the two north ends of magnets together. That makes the magnets very unhappy. They don't like that. And so it's these kind of systems where we see frustration, and artificial spin ice is a very good model of that, because I think the Kaguma in particular, possibly, I'm forgetting if it's Kaguma or square. I think it might be square, but we have kind of intrinsic frustration in that there is no kind of perfect way to order these spins. There will always be some kind of remnant frustration in the system. And so that's really interesting, because it's also what we see in ice, for instance. There is no kind of perfect way to order the ice that there will be no frustration.
Got one more question from Susan. When you test at larger sizes, do you test just at the best field strength or at all field strengths?
So that one in particular, we were just testing. So we just took this one and we tested it at its own field strength. Yeah. But in general, if it works at this field strength, then it kind of works at all the ones before. And in fact, that's not necessarily true, but it is true for these data at least. For instance, I took this one here and I found that it got perfect score here too. So even though we weren't able to achieve a perfect score, we found one here that did here as well. So hope that answers the question.
We've got another question from Gunnar. Have you considered 3D models?
Yeah, well, so the answer to that is I would like to. The simulator we have at the moment doesn't allow for 3D models, but yeah, there's definitely a lot of interesting things you can do with 3D models, especially in terms of kind of computation. It allows for much greater degrees of freedom. That's one of the most restricting things about these 2D lattices, is the weights you have between the magnets are very constricted positionally. So yeah, 3D is very exciting, but we don't quite have the technology yet to simulate it, but I think we might have that possibly soon.
I've got a question as well. I can't remember if you said it, but do you have a single tile, or can you have a group of tiles that you
Yes.
can...
Sorry, continue.
Did you hear that?
Yeah, sorry, I cut you off.
Yeah, yeah. Do you have a group of tiles that you can, an individual that can have, and then maybe you can decide where each tile is placed next to, I don't know, its coupled tile or something like that?
So it's kind of through this, you kind of get that. So like I said, individuals are generally sets of tiles, multiple tiles.
Okay.
But and kind of through this symbolic process, you can kind of do things like that. So for instance, if you place this tile, these magnets also have symbols. So if you place this A tile and this magnet is a B, then the next tile you place is going to have to be a tile that starts with B, for instance. So you can kind of use this symbolic way to kind of get things like that into your system. Yeah.
Could you also, once you start to understand maybe a smaller system, that then becomes a tile or something like that, so you can have these subsystems that then...
We have the restriction here that a tile has to be only 2 magnets. So so we can't do that for this, but I'm exploring things like where you do build a small system and then just kind of tessellate that system, for instance. So I think that could kind of achieve what you're talking about there. Yeah.
Okay, great. Cheers, Arthur.
No problem.
We